going to eliminate the coefficients for y and replace them with those constant terms on the right-hand side of the equal signs. I'll do it properly, correctly. And I'll refer to this as d sub y. It's just that when I compute, I get nothing more than, is that a 38 minus 44? Which in this case ends up being, I can't do it. -6. Positive 6, apologies. Negative 6, isn't it? My goodness. And my solutions for x and y are going to be as follows. They're going to be nothing more than the ratio of d sub x to d and the ratio of d sub y to d. In this case, that would be -2 over -2 or -6 over -2. Or shall I say, it's my solution to the system is merely the order pair 1, 3. It's just a whole new technique for solving system equations. So now that I've done that, I'm just curious, have I jogged other memories? Let me see a show of hands again. You've seen this before. But shoot, you guys, I don't like my example. It's too easy. So if you don't mind, I'm going to apply a whole new technique to my example test, which I've gotten rid of. Hold on a second. Hold on. I know I'm not bringing it up on the screen, but here's the same system we saw over and over again. As an equation, I've got a 2x minus 2y minus 4z equals this. My second equation is 2x plus 1 minus z being equal to -3. And then I have an x plus y plus 2z equal to 5. You guys, I'm not using the same example for root step. I'm just using the same example so you can feel comfortable that we're generating the same solution as we go. So Cramer's rule, I'm afraid, becomes a bit more complex because I'm going to have a 3x3 system now to deal with. So, giving myself a bit of room. I think my coefficient matrix B, I said matrix, didn't I? My apologies. I meant to say, I'm going to now create my coefficient determinant, not matrix. And my coefficients are 2, -2, -4. 2, 1, -1. Is that a 1, 1, 2? It's just to evaluate a 3x3 determinant is a pain in the rear end, so I give up. And I rewrite this as an expression involving 2x2 determinants because they're a piece of cake. So, here's what I'm going to do. I'm going to take any row or any column, I do not care which. How about the first row? And list what I refer to as my cofactor expansion. Now, to list my cofactor expansion, what I'm going to do is take each and every one of the numbers, 2, -2, -4, and I'm going to multiply them by a very particular 2x2 determinant. However, when it comes to that very first entry, 2, let's talk about its position. That's in the first row, first column, isn't it? Take 1 plus 1 and you get 2. Raise -1 to the power and you get 1. Well, -1 to the second power is 1. Positive 1, no sign change. Notice, however, the -2 is the first row, second column. And when I take its row position and column position, add them together, raise -1 to that power, I get -1 to the third power, which is 1. -1, shoot, I'm going to get a sign change. And for this one entry over here, the -4, it came from the first row, third column, but when I add the row and column position of 1 and 3 and get a positive 4, raise -1 to the power, I don't get a sign change. And the corresponding 2x2s I did not get right in are the following. Take 2's row and column and eliminate them. And look at the 2x2 determinant. Let's go scan. Isn't that nice? Take a peek at -2's position. Well, that was the first row, second column, but if I eliminate the first row, second column, doesn't that leave me with this 2x2? 2 -1, 2. You remember this? I take -4's row and column and eliminate them, I think here's the resulting 2 by 2 determinant. This remains standing. Is that a 2-1-1-1?
Wait, is this Cramer's rule?
This is Cramer's rule for solving the original system.
I just didn't know it was called Cramer's rule.
And I maintain my arithmetic life is a piece of cake now. Because arithmetically speaking, I think that gives me 2 times a number, plus 2 times a number, minus 4 times a number, where those 3 numbers are just the evaluation of 2 by 2 determinants, a piece of cake. The first one is
3.
The second one is
5.
the third one is
3.
say it again.
1. 1.
Or shall I say, is that a 6 plus 10 minus 4? Or shall I say 12? Chris?
Are you going to ground this in some really nice theoretical framework?
Oh, yes. Yes. I was just kind of hoping tonight you don't look at theory. Go home and practice with the nuts and bolts, and then I'll talk about all the machinery for the theory tomorrow. That's what I was hoping. Now, I will call this big thing B. And what I want to generate next is, as you can probably imagine, D sub x. And D sub x is going to be nothing more than the original D. It's just the coefficients for the variable x are going to replace with the constant term on the right-hand side of my equal signs. And I think in evaluating D sub x, I generate this, a cofactor expansion about any row or column you like. I just got to worry about sign changes. Let's do the first row again. Is that a -6? Times the 2 by 2 left over is going to be 1, -1 2. Plus a -2, but I get a sign change because it's position. Times this 2 by 2 when I eliminate -2's row and column, but that would just give me this 2 by 2. -3 and -1, 5, 2. And finally, plus the very last entry in that first row, which is -4, excuse me, I should say -4. Times the 2 by 2 I generate and eliminating -4's row and column, but that just gives me -3, 1. No, positive 5. Here too, arithmetically, life's a piece of cake. I think that just simply gives me -6 times a number, plus 2 times a number, minus 4 times a number, and here are the numbers. They're going to be 3. Is that a -1? Is that a -8? Or shall I say -18 minus 2 minus, or excuse me, plus 32? Is that just going to give you positive 12? Did you guys see where I'm going with these? I need an ordered triplet solution. But clearly, x as a component of my solution is merely going to be the ratio of this to this. But in this example, that's just the ratio of this to this. There's the x value for the solution. This is, what did we get last time? Didn't we get 1, -2, 3? I think. Well, for my d sub y, I think here too, it's nothing more than the original d coefficient matrix. It's just this time, for the y coefficients, I'm going to replace those with the constant terms on the right-hand side of the equal sign. What remains standing is everything else in the first and last columns. So let's evaluate. Does that give me 2 times this? Plus a -6, but with a sign change, times 2 -1, 1, 2. Plus a -4 times this 2 by 2, 2 -3, 1, 5. But that's 2 times something, plus 6 times something, minus 4 times something. Let's talk about the somethings. I think the somethings here are going to be, is that a -1? Is that a 5? And is that a 13? Give me a -2 plus 30 minus, yikes, I don't know, is that a 52? Is that a -24? So I guess that's going to suggest that y is a ratio of d sub y to d, but that's just a ratio of -24 to 12. Oh, look at that. I got -2 again for my export. And I can play the same game to generate the y-coordinate. Do you mind if I don't? So I think you guys get the idea.
Question on notation, when you
Yes.
have just the straight lines, does that represent determinant rather than bracket?
Yes, and so I'm being very careful with my notation. So just a straight line is I'm referring to a determinant, which should evaluate to a real number so far this semester. Later this semester, I'm actually going to change it. So you guys, check this out. I said in English that it's really easy to compute a 2 by 2 determinant. The arithmetic's not bad. Product on the main diagonal minus product on the non-main diagonal. But for me to evaluate just one of these 3 by 3s, when I list the cofactor expansion about the first row, notice that in doing that, I ended up generating 3 2 by 2s I had to that I had to create. So imagine what's going to happen if I evaluate a 4 by 4 determinant. Cofactor expansion, I get 4 3 by 3s. But each of those 4 3 by 3s has 3 2 by 2s in them. That brings it to 12 2 by 2s confused. Do you see, Brad, I'm picking on you because you're the computer science person.
Well,
Can you appreciate how my efficiency is really declining in terms of an algorithm?
well, so if I was programming a matrix, I would put everything in, or work everything into reduced row echelon form, and then just put the answers, right?
Mm-hmm.
That'd be the best way to do that. But with something like this, it's just nice numbers all the way through. I mean, that's the thing I like about it. I'm not working with a giant matrix full of fractions or something.
That's why when you watch me do this on the board today,
Yeah.
I can go through my arithmetic pretty easily, and I'm really
It's
bad
so
at this.
clean and pretty.
Because I can keep track of the numbers
Yeah,
better,
yeah.
as opposed to dealing with augmented matrices.
Yeah.
That's my opinion. You guys, so far so good. If that was okay, and check this out. If I were to list a cofactor expansion about the first row, that would give me 2 times this, plus 3 with a sign change times this. I'm losing track of where I'm at. Can you tell me what's next?
Plus 1.
Anybody?
0 1 0 0.
Plus too much work.
Yeah, 1. What's that?
Oh, the determinant just to be 0 of that last 2 by 2.
Yeah.
You know, you're right. I just think you could do better than that. I think you could say, instead of listing my cofactor expansion about the first row, what about the first column? Isn't the cofactor expansion about the first column going to give me 2 times this 2 by 2? Plus 0 times another 2 by 2. Who cares what it is? Plus 0 times another 2 by 2. Do you see my point? Since this first column contains zeros everywhere except for the first entry, I think by far it's much easier to list a cofactor expansion about of whatever row, whatever column that has.
So you could just solve
Zeros
that
everywhere else.
just by taking it out of the matrix as it is, like that.
Absolutely. What's
Yeah.
my final answer? Don't blink. Say no.
Well, you need the answers, but you have 3x or 3z down there, and so you can figure out
Right.
what z equals easily.
You're right. I wasn't going that far though. I
Yeah.
wasn't actually looking at a system of equations. We're simply evaluating a 3 by 2 determinant.
Okay.
So I wasn't talking about an original system of equations. You guys, in that case, again, be selective sometimes when you have a bunch of zeros in your matrix or determinant, excuse me,
Yeah.
and evaluate a higher determinant.
So you can actually evaluate a determinant like that, like just by taking the cross products? Or I shouldn't say cross products, but multiplying 2 by 3 and subtracting it by the other diagonal. No, you can't do that, can you? No.
I'm
Did-
not sure I understand what your question is.
All right, can you show me the steps that you took in your head to get that?
Did you get this right here?
To get 6.
Product out of the main is 3.
Okay.
Minus 0 is just 3. 3 times 2 is 6.
And then you just didn't evaluate the other ones because they just equal 0.
Sure, the coefficients are going to be 0,
Okay,
so who cares?
okay.
That was my whole point.
I see.
Can I make it even better? If it's an upper or lower triangular matrix, it's just a product down the main diagonal. That would be the valuation determinant. Like pretty easy in that case?
Yeah.
cofactor expansion should I do now? First column, first row,
Bottom third.
bottom third row. List a cofactor expansion, and I think you're gonna get a 1 times a 2 by 2, which in this case is 2, 8, 1, 3. I want an answer about this though. Do I get a sign change?
What's the rule about the sign changes again?
And here's the rule about the sign change. It's the following. You identify the position of this entry on the outside for which you're creating a cofactor expansion. Identify its position in terms of row and column. I think its row is the third. Its column is the second. You take its row position, column position, you add those entries together, you get a 5. -1 to the 5th power is -1, so I get a sign change. Treat that as a coefficient outside of the mess you already have here. And I think in the end, you're just going to get -1 times, is that a 6 minus 8? Or shall I say, -2? Or how about this? How about a 1, 2, 4? 1, 2, 3. 0, 1, 0. You guys okay with this? I'm going to be quiet.
Yeah. Not okay with that. You made a big mistake.
Did I really? Where?
Your
Oh,
determinant is half a matrix.
Thank you. I made a big notational mistake. Yes. Well, something interesting about my last 2 examples is that I gave the same determinants. It's just that when it came to the very first row over there, I didn't have that extra factor 2. So notice how taking that determinant, multiplying the first row by 2, gives me an extra factor 2 to the entire determinant. Unlike with matrices where I'd have to put a 2 into every entry. Michael?
You just got the determinant you used. Where did the 1 and 3, or actually, how come they're arranged in that order? Like, where did you pull those from?
So are you referring to these numbers right in here?
Yes.
Here's what I did. Since I was listening to cofactor expansion about this entry right here, I eliminated one's row and column, and I looked at the corresponding 2 by 2 that remained standing.
Okay.
That's where the 2813 came from. Chris?
Did you just do something interesting?
Yes. And here's what it is. I think you can take a determinant, and if you multiply any row or column by a constant, the determinant's multiplied by that constant. And this example illustrates that, but I'll prove it to you. I'll prove it to you. Maybe not today.
Say things like that, I could get a little nervous.
I lost my numbers, my 7. You guys tell me what to write.
Couldn't you just simplify that before you started writing all this?
What do you simplify?
Well, you have like e to the x in the numerator, and then you got 2e to the x right underneath it. I mean, you could just knock some of those out, right? E to the x, and then right underneath it. So, I mean, if you just do a couple permutations, you can simplify it before you go into Cramer's rule.
Are you thinking that this is some kind of system of equations? Because I never said I had a system of
Oh,
equations. It's
okay,
just a
okay. No.
matrix.
Okay, never mind.
So you have an entire row.
Yes.
Multiplied by e to the x. And if we factor a single row out, we can say something about the resultant determinant.
And what is it?
That is multiplied by whatever factor 1.
1.
E to the x.
E to the 2x.
2, 3 e to the x, and e to the 2x. And we got 1, negative e to the x, and negative e to the 3x.
2x.
2x.
Yeah.
But it's not a determinant, is it? It's a matrix. If it were a determinant,
Is that legal?
It's 100% legal.
Prove it tomorrow, I guess. E to the x. And we keep doing that.
How many times?
I would say 3 times.
So
Twice.
twice.
What?
Thrice.
Right.
Where'd you end up with a one?
But you have to keep doing
E
that.
to 3x then?
No, I was asking a simpler question. You guys watch. Here's my question. If equality holds, then what's on the outside?
Yeah.
Well, I pulled the e to the x out of the first row.
Yeah.
So there's a factor of e to the x. But I pulled one out of the second row. I pulled one out of the third row. I think I've got 3 such factors of e to the x. Unlike a determinant, I only pull out of a single row or column. Whereas with a, I think I misspoke, sorry. Unlike a matrix, I pull a factor out of a single row or column. But since it did it out of 3 columns, I got 3 of them on the outside. Very unlike what happened when I pulled e to the x out of a matrix, because with matrix, if I can call it the scale of multiplication, I've got to pull something out that's a common with every one of the entries inside the matrix. Big difference.
So what if you pulled out a different term from each row?
That is perfectly fine.
How would you write that?
Oh, piece of cake. Let's do it.
Would you just multiply them all together? Or? Two, 4, 6, 8.
So how can you simplify this? What would you pull out?
You pull out an e to the x from the numerator. You pull out an x, or not the numerator, the top
Yeah.
row, this x from the second row, and a 2 from the third row.
And what remains standing is just a 1 e to the x, e to the 2x. Is that a 1x x squared? And then finally a 1, 2. So I simplified my determinant.
But if you multiply, or if you look at it multiplied by like that, so how would you plug those numbers back in? I guess is what I'm saying. Do you just look at them in order?
Holy cow.
Yeah.
I'll put them in any way I darn well please.
It's going to be the same thing, right? Oh,
Not
okay.
necessarily. I can put them back in any row or column I darn well please. Just pick a column, pick a row. Or I could divvy them up.
So if we mosey back on to the other one you were doing right there.
You mean
Yes.
the one over here?
Yes, sir. If you just pulled another e to the 3x, and you could just simplify that into coefficients, whatever you had there, right?
I'm sorry, I'm just tired. Can you say that again?
You skip right to e to the 6x times the determinant of, 1, 1, 1, 2, 3, 1, 1, negative 1, negative 1, just by pulling it out a row at a time, or excuse me, column at a time, right?
Absolutely. What he's saying is this. Take this one step further, pull out a factor of e to the x from the second column. Oh, simultaneously pull out a factor of e to the 2x out of the third column, and you're going to end up with the end e to the, is that 6 of 1, 1, 1, 2, 3, 1, 1, negative 1, negative 1.
Look at that, yeah.
If you guys are checking my arithmetic. I can take it as far as I darn well please. Absolutely. Anybody else? By the way, don't be careful, don't do any work. But if I were to evaluate this 3 by 3, what would it be? What dimension would the matrix be?
It wouldn't be a big
It wouldn't be a matrix, it would be a real number. So in the end, I think the evaluation of that 3 by 3 determinant is nothing more than a scalar function, namely some constant times, e to the 6x. And we will be using matrices or determinants in this fashion when we actually solve higher order DEs. Chris?
So, and how much time is it going to be that we're going to learn something? I won't say awesome, but awesome. Just the next jump in sports.
I think when you and I are finally done talking about linear algebra for the most part, when I come back to solving higher order DEs, then I'll be using these determinants with a technique called variation of parameters. And that'll be significant. But I'm going to have to take a break, a long break, like a few-week break, and really look at linear algebra first.
Going back a couple of examples where you showed us that an upper or lower triangular, it was a determinant, but you said an upper or lower triangular matrix the product down the main diagonal is the solution?
Then sir, if I said that I misspoke, I meant.
It's only with determinants, right?
Yes.
Not with matrix.
Yeah, I guess I can fix my English by saying, look at the corresponding determinant from that matrix. And if you've got an upper or lower triangular determinant, then this computation is merely the product on the main diagonal, that's its evaluation.
But that doesn't work with matrices.
No, because a matrix is just a rectangular array of numbers, it doesn't end up being a number itself.
What chapter are we in here?
I have no idea.
Are we still in 2? It looks like 3 is all about determinants.
Yeah, this is diving into chapter 3.
It's diving into chapter 3? Awesome.
You guys, what else can I say about this before I stop? So we have so far done. Three techniques for solving systems of linear equations. And if you guys don't mind, can I stop talking the number crunching business? So tomorrow when I come to class, can I start talking about the theory of why it's all true? Understand the workings of it. In my past, when I've done that initially, I tend to think I push students off of the whole notion of these determinants, because a lot of students are taken back by the actual definition. So if you just get practice tonight, not let it slide to the weekend, so that tomorrow I can be more theoretical. That'll be the best thing. So let's talk homework. I am afraid for tonight I am all over the place. So hold on. So in section 2.6.
This is all over the place.
Yeah, or just do something to one.
To one row,
Or two rows, and then you get a new matrix.
You go through the whole process.
I think I have 18 to 25 off.
17th or 25th?
Yeah, but 18 is not odd.
19.
So,
You can think of it, 18 as an odd kind of number.
Not very mathematical, Mr. Donovan.
No, it's not very mathematical.
he's a mathematician. He can call anything odd that he wants.
No, I can't. Not 18.
I can't find, oh, here it is. So in section 3.3, take a peek at these. Not a lot. Nothing theoretical, just number crunching, that's it.